So the sp3 carbon keeps this from contributing to, yes, Devin just said it can't be used in resonance, and that's exactly right. If there is an atom that's preventing resonance forms from being created through the double bonds, you know that that atom is a problem and it's keeping it from being a conjugated system. How would you describe this system? What's the word that was used in the notes?
Isolated.
Right, yeah, so this is a diene, but it's isolated, right? So when we're looking for conjugated systems, we are looking for a repeating pattern of double bonds. Okay, and then one more. I know these are the exact examples that were in the notes, but I want to make sure that we're all on the same page here. Is this system conjugated?
No.
No. Okay, so I heard some no's. I see some no's in the chat. No, this is not conjugated. What do you call this instead?
Commuted.
Close.
Have I,
In the chat, cumulated. Yeah. So this is considered cumulated. What is the hybridization of this right here?
SP.
Yeah, it's going to be linear. So that's our issue here. Okay. We're good on cumulated versus isolated versus conjugated. You feel okay? Cool. Okay, so the next thing I want to look at are reactions of conjugated systems. Okay, so we're going to start off kind of simple. This is not the exact example that was used in the notes. There's kind of a very small added complication here. Okay, so go ahead and copy that down. And then in a second, I'm going to break you up into breakout rooms. And I just made you a co-host, so I think that that should keep you from getting assigned into a specific breakout room.
Okay, sounds good.
Yeah, we're gonna find out. So then you and I can both hop through a couple different rooms. Okay, so I'm gonna break you guys up into 12 rooms that should have 7 to 8 people in it. So go ahead and join them in a second. I'm gonna give you about 4 to 5 minutes to think through this. When I close the rooms, it gives you a 1-minute countdown. You can stay in that room for the entire minute if you need it. You do not have to leave just because I've ended the breakout rooms. Okay, and also Anne and I are gonna be hopping through the breakout rooms. Oh, Anne, you did get assigned. So you might be able to move yourself though. So we'll see. So yeah, Anne and I are gonna be hopping through the rooms and we really want you guys participating. So if we come into a room and it's completely silent, that's not what we're looking for. I want you guys working together. I want you talking about it and everybody should be participating. Otherwise, there's really not a point in being here, right? So I'm gonna open the rooms.
Dr. B, I think you're muted.
I got it. What type of reaction is happening in the top line?
We were guessing it was going to be a 1-2.
1-2 kinetic. Yeah.
Right, yeah. So this should be a 1,2 addition. It should be Markovnikov. Is there just one product that would form?
Or 2.
Wouldn't it be a 1,2 addition and a 1,4 addition, but with
Yeah,
different
so
percentages?
the top one is going to give you a couple different 1,2 addition products. Sorry, I see a question in the chat. The question is about not being able to hear anything. Would somebody mind responding to that to check their audio settings while I keep going? So the top one is a regular 1,2 addition. So you should have some Markovnikov addition, and you should have more than one product. The bottom reaction is heated to 75 degrees. So what type of reaction are we going to see here?
1
Oh.
addition.
A 1,4.
1,4 addition.
Right, we should be seeing a 1,4 addition.
So I was gonna ask also, it says in the book that the 1,2 addition occurs in -80 Celsius, and then the other one occurs 40 degrees and up, I believe.
Yeah, so definitely if you keep it down to -80 degrees Celsius, you're going to see like almost complete 1,2 addition. But in the lecture notes that I gave you guys, I showed, I believe, a room temperature reaction, and it was like 78% 1,2 addition and a very small amount of 1,4 addition. So I don't love to give you guys like temperatures to memorize. So what I kind of say is like room temperature or below, go ahead and assume that the major product is 1,2. That doesn't mean it's going to be 100%, but it will be the major product. If it's heated, we're going to assume that the major product is 1,4.
I see.
So you'll see very specific examples in the textbook of like this very specific reaction and at these specific conditions will give you exactly this percentage of this product. And I don't like you guys to try to memorize those types of things. I want you to understand the situation as a broader situation, I guess. So, okay, in the first one, it's a 1,2 addition. And if we were to number these carbons according to naming, these would be carbons 1 and 2. Does this mean that this is the only place that we can do the addition?
No.
No, because 1,2 addition just means that we are adding the hydrogen and the bromine next to each other, right? They are going across the same pi bond. Whereas 1,4 addition means they are separated from each other. So it can also be 1,2 or 1,2. What you have to do is go through and figure out which carbocations can be formed, and you're looking for the best carbocations. Yeah, I'm going to erase all those numbers just because those are kind of obnoxious. So let's draw out a couple different options. I'm going to use some different colors. So if we were to protonate the first alkene, which carbon does the hydrogen go onto? Carbon 1 or carbon 2? And we're gonna call the carbons by their nomenclature numbers right now.
Carbon 1.
Right, okay, I'm seeing a lot of ones in the chat. Why does it go on carbon 1? What does that do for us?
It's least substituted.
Yeah, that is the least substituted carbon. That puts the carbocation on the most substituted carbon. What else is good about this carbocation?
The
What would you call that position?
Final.
allele? Is that the
Allele.
allele?
Allyl, right, yeah, this is the allyl position, right? It's one removed from the double bond, which means this carbocation is resonance stabilized. So that makes this a superior carbocation in a couple different ways. Okay, so that's one carbocation that we can get a product from. And if we were to draw out the product, I'm going to draw it here, so we'll have to take our other reaction down lower. Our product from this carbocation would put the bromine here, right? Because the bromide is then going to attack the carbocation. Okay, if we We'll pick a different color. Let's go orange. Now we want to protonate our second alkene. Which carbon should the hydrogen go on?
Four.
Yeah, so I see 4 in the chat and I heard it out loud. Why do we want to put the hydrogen on carbon 4? It's not more substituted than carbon 3. What is this carbocation that this one would not be?
Allelic.
Right. We want the allyl carbocation. So that's why we protonate carbon number 4 instead of carbon number 3. So then our product from this is going to look like that. So we have a mix of products here, right? We want to go through the allyl carbocation. That is the important thing. Okay, so let's look at the second reaction. So the second reaction is going to be a 1,4 addition. I'm gonna go ahead and draw the alkene out again. So in this situation, we have to decide, where are we going to protonate and where are we going to end up adding in our bromine. So we know that in a 1,4 addition, you're going to have to protonate one of the exterior carbons, essentially. Like the hydrogen has to go on one of the outside ones so that we can end up with the 1,4 addition scheme here. Let's keep our same numbering scheme. And instead of actually, just asking you outright, which one is better, let's just go ahead and draw both options. So let's say that we protonate on carbon number 1. It would give us this same carbocation that we drew up here. What happens so that we can do the 1,4 addition?
A shift?
Yeah, kind of. So it's just a resonance form, right? We are moving the carbocation around, but we're just going through a resonance form to do so. So our hydrogen is still over here. The double bond is here. And the carbocation has moved to here. So then when we put the bromine on, we end up with this product. Does that product look any different from something else that we've already drawn? Not really, right?
Like flipped only?
These are actually the same molecule. So the important thing here is to go through the mechanism and understand the idea. If we protonate carbon number 4 instead, we would start off with this carbocation. And the only thing that's really different with this is that if you start off with this carbocation, your resonance form is going to show an allylic carbocation that's also primary. So this is the less likely product to form. But this would actually give you a different product from one that you had seen above. So this product would probably be the minor product of this reaction. But it would actually give you something different. Okay, so this example is kind of weird because we didn't draw out something, super different or anything like that. But I want you to spend time drawing out those carbocations when you work on these types of problems. Before we run out of time, I want to look at Diels Alder for a second. That's also going to be, we're going to spend a ton of time on Diels Alder on Friday. So we're going to work through a bunch of 1,4 edition products and a bunch of Diels Alder reactions on Friday. But I want to introduce it and make sure that we understand those stereochemistry rules. How many people actually made it to that part of the chapter? Yeah, that's okay. I didn't ask you guys to do that, so that's perfectly fine. I see a couple people did. Okay, so the Diels Alder reaction is really, really interesting. I'm going to draw out just something really simple to get us started, because I know that a lot of us didn't get to it yet, and that's perfectly fine. So one of the examples that's given in the notes is this one, you have 1,3-butadiene and ethene. And if you heat this up, I think the conditions were like 200 degrees Celsius, and it has to be in a sealed tube, so it has to be under pressure. But if you do that, what you end up with is this kind of concerted reaction where all of your electrons are moving in a circular pattern. And ultimately what you're doing is creating new bonds between these carbons. So your product ends up being cyclohexene. And these are your new bonds that you formed. So these carbons are from your 1,3-butadiene, and this is from your ethene. So this reaction is kind of bizarre, but it's really cool. And there are a lot of kind of confusing stereochemical rules about this that I want to kind of generalize with you guys real fast, because I think watching the videos and reading about it on your own is kind of confusing. But it's actually, it's one of the few things in organic chemistry where there are just these really nice conventions where if you can remember them, you can draw the correct product every single time. So, let's have this as our diene. So the Diels Alder reaction is always made up of two parts. You have a diene, and then you have another species called the dienophile. So this is the thing that the diene is interested in, and the dienophile is diene loving or diene seeking. So they are just meant to react. You want electron donating groups to be present on your diene. So that's why I picked methyl groups for this structure here. Alkyl groups are electron donating. And on your dienophile, you want things that are electron withdrawing. So I'm going to draw something very generic right now. I'm just going to write electron withdrawing group. Now, the other thing about Diels Alder reactions is that the conformation of all of the reagents is held through the product. So we're going to draw a couple things here. You have these substituents that are pointing outside of the dienophile, so pointing away from everything else. That's part of the reaction. And they are called the outside groups, just by common convention. And the substituents on these carbons that are pointing inside, like if you were to draw a ring, they would be part of the ring, are just called the inside groups. Now, the reason this is important to know is that the common convention here is that there are two types of products that form in Diels Alder reactions. The major product is the endo product, and the exo product is the minor product. Now, the rule for drawing the endo product is that in the endo product, the electron withdrawing group and the outside groups are pointing on the same face of the cyclohexene. So they are pointing in the same direction. They're all cis to each other. And the common convention is to put your outside groups down and therefore your electron withdrawing group down. So you draw out your cyclohexene, you draw your outside groups pointing down, you draw your electron withdrawing group pointing down, and you draw whatever is on the inside pointing up. And that is going to be your major product, and it will also have an enantiomer. You can draw the enantiomer really easily. You can either switch the orientations of everything if you want, or you can keep the orientations the same and simply change which carbon your electron withdrawing group is on. These are both examples of your major product. Your minor product would be different in the sense that the electron withdrawing group would be going opposite of your outside groups. So my electron withdrawing group would be going up. So again, I know I've said the word common convention about 100 times, but this is the way that Diels Alder is taught because it is the most straightforward approach. The tricky things come into play when you have multiple and different substitutions on your dienes and dienophiles. So if you have an electron withdrawing group and an electron donating group on your dienophile, the complication is that you just want to make sure that the electron withdrawing group ends up on the same side of the outside groups from the diene. So I want to give you a specific example because it's 10:40, so we have 10 minutes. I think we could probably like together work through 2 more examples of this. Is it okay if I clear this screen?
Yep.
We are recording, so you can always, again, watch this later. I will not forget to post to YouTube before I leave my office today. Or at least I'm hoping I won't. I'll try not to. So, here is your diene. Actually, sorry, I meant to make this carbon go a different direction. So here's your diene. We have an outside group and we have an inside group. We're going to add your dienophile. So we have some extra stuff on here, but the reaction is still the exact same. So I want to give you just like a minute. Go ahead and identify your outside groups, your inside groups, and then try to draw the major product. Just take 1 minute on your own. See if you can get this. I know this is brand new chemistry. Okay. So we're gonna go through this together. The other thing that I want to tell you guys is I want to do kind of an attendance thing again. Go ahead and private message me when you get a second, one question that you have from Module 12. So private message on Zoom, just one question that you have from Module 12. Maybe something that you didn't understand, or if you felt really good about Module 12 and you're confused about Module 13, send me a question that you have about Module 13. So just one question that you have. Okay, so I'm not a huge fan of shortcuts, but Diels Alder kind of screams shortcuts. There are a lot of really nice ones that can just help you visualize the product before you really draw it out. So these carbons are the ones that are going to be attaching to the diena file. So you can visualize that your new bonds that you're creating are going here. And the base of your product is always cyclohexene. So if you can see that cyclohexene, you can draw everything else coming off of it. So your cyclohexene comes from these 4 carbons. Your double bond ends up getting put here, and these 2 carbons here. So we have an outside group and we have an inside group that are going on these carbons. Which direction do I want to point my outside group? Up or down?
Down.
Down. And which direction do I want to point my inside group? Up. Right, so that part really is that simple. The next thing that you have to do is identify your dienaphile carbons and draw the rest of your dienaphile on here. So I added the complication of this methyl group here. It's the right-hand side of this that is the electron withdrawing portion. So when I'm drawing the bonds to the rest of this cyclohexane, which direction should those bonds be going? Should they be going up or down?
Up.
For our major product,
Down.
yeah, remember that we want them going in the same direction as our outside group. So we want to draw those bonds down for our major product. And then you can draw your carbonyls on there. And then what do we do with the methyl group over here? Which direction is it going to go?
Up.
Up. Right, so this is one of your products, and then you're going to have another. And usually when you're being asked a Diels Alder question, the question is phrased as, what is the major product of this reaction? So most times you do not need to be drawing the exo product. We're just looking for the endo product. And in this case, this is what I would want you to draw. As long as you draw one of them, I'm fine with that. If I ask you to draw both enantiomers, you draw both enantiomers. Okay, let's do one more. We only have 3 minutes. But I want to get this in your heads so that you can work on your homework through the week. Okay, this one takes a little more thought. Both of these would probably require some heat. So remember that your conformation is retained into the product. So earlier we saw something that was cis and we drew it cis in our product. This is trans. So you want to make sure that you draw it trans in your product. Miguel, I see your question. I'm not sure I understand your question. I think it's referring to the current problem, but if not, that's okay.
Like, can we rotate the bottom portion of the right side so to make it look how can I say it, like the problem on top?
No, you can't. So since that's a double bond, it is locked into the trans conformation. So unlike up here where you have the single bond connecting the two double bonds, this is called S cis, and this is also in the S cis conformation because it's a ring. You can do some rotation there, but you can't rotate around just a regular double bond. The only thing you could do is rotate around this single bond, but that wouldn't change the trans conformation. Okay, so we only have 1 minute left. So we're gonna go ahead and draw out the solution to this. So remember that you're gonna have a cyclohexene base of your product. Now, since our diene is cyclic, everything is automatically on the inside, right? These are automatically inside substituents. So you're going to point that up. And drawing bicyclic structures is often really challenging for students, but it doesn't have to be. So you're just drawing a 6-membered ring that includes these 2 carbons. So you just have to draw in those 2 carbons that are part of the ring. I just said it's not challenging, and then I drew like the ugliest thing in the world. Draw those 2 carbons and then connect them. And if you really want to indicate that it's pointing up, you can give it a little 3D action if you want. That's all you have to do to draw a bicyclic structure. You can also draw it from the side, which we can practice on Friday, but I want to finish getting this in. So these are our dienophyl carbons, and the aldehydes are trans to each other. So one of them can be down, but the other one is going to have to be drawn up. And so that would be your major product plus the enantiomer. Okay, so by Friday, you should have gone through the entirety of chapter 13, and you should be working on those 1-4 addition problems and the Diels Alder problems. I'm going to send out some copies of old quizzes that I've given. I think you're going to take a quiz through Canvas this week. I want to draw my own problems, which I can also do through TopPat. I'm going to think about it. There are issues with both, which is why I'm kind of, it's a toss-up, but I'm going to draw my own questions, so they will look like the quizzes that I'm going to send to you guys. And one of them, I also have a talk through key that I did for my students when I taught this last spring. So yeah, definitely spend some time on this. On Friday, we're going to do problems where if you did not read the chapter, Friday is just not going to go well for you. It's going to be very, very frustrating. So I'm going to stick around. Class is over, but I will still be here if you need to ask questions or anything like that.
Also, just a reminder, SI begins this week. So if you sign up for the Monday session, it is today at 1. So I look forward to seeing you guys.
Awesome. Yeah, and you're gonna do some OCHEM 1 review?
Yeah, I think majority of this week I'm gonna do mostly OCHEM 1 review and then I'll also do oxidation and reduction agents. I feel like that's pretty easy. And then next week I'll focus more on like Diels Alder. Are you guys doing next week? Is it aromaticity?
We will get to it. Yeah, we're
Okay.
gonna start identifying aromatic compounds. Probably, we'll probably look at it on Monday, and then the problems will still go over some chapter 12 and 13 stuff.
Okay, yeah, but I'm just gonna try to focus more on OCHEM 1 this week to get refreshers for everybody.
I see a question about signing up for SI sessions. You were supposed to fill out the survey that was sent out. Can they still sign up if they didn't yet?
So the survey closed on Thursday. I sent 2 reminders for that, but if you didn't get it, you need to email Victor or Lindley. They both are the head of the SI program. You can find their information on the Slack website, and you need to email them that you didn't get into the survey, because I can't assign you guys into, I don't have access to that, so.
Yeah, and their emails are also in the syllabus, so you can find them easily there as well. And they're both very, very friendly. So it's easy to email them or talk to them. Are there any other questions?
Dr. Viziger, I have a private question to ask you. But
oh, sure. Yeah,
after
if you
everyone
want to
leaves?
stick around until your other classmates have left, you're welcome to do that.
Okay.
I had a question about the module. I sent it over the module discussion board because I went to is that just a technical thing that I need to send to Top Hat? Because
yes, yeah. Sorry, I responded to you last night. So I think you posted it last night.
Yeah. Yeah.
So yes, please ask Top Hat about that. I've heard kind of similar things from other students, but also about the homework. So I'm also going to be asking Top Hat about that. But it's weird because it doesn't seem to be happening to a lot of students, but it's happening to some of you guys, and that's confusing to me.
Okay, yeah, because I wasn't sure if it was because I had left and logged out and then came back and finished it, or whatever. So okay.
Is it just the reading questions, or did you also have that problem with the actual homework assignment?
So I went to do half of the homework problems, and then there was some other questions that I wanted to review, so I didn't finish all of them. But when I went to go look for the graded stuff in terms of the quiz and the reading in-text stuff, it said all of it still needed to be graded. It said just ungraded.
Oh yeah, so that just means that hasn't been released to the class.
Okay. And then my other question was just, I don't know if she answered it. For the SI, if it's all the Zoom, if all those meetings are under the same Zoom meet number.
I'm not sure, but I am going to post the Zoom links after class today on our Zoom link thing, and we'll make it clear on there.
Okay, thank you.
With the Zoom links yet.
Okay, thank you.
Mm-hmm. Mo, I saw your question. I already forgot it though. How do you sign up for Examity? So I have to set those exams up with Examity first, and then you can sign up for it. For some reason, there's a disconnect between our Canvas site and Examity. And so when I tried to create an exam, it let me, but it didn't connect to the class. So I'll send out an email when those are actually available. Okay, I see the other questions I see, oh no, you're not behind. The other questions that I see seem to be the private ones. Okay. Yeah, so if nobody else has any questions, you're welcome to go. Yes, Megan?
Sorry, it was more pertaining to me because I have like appointments for my kids like during the week coming up in, especially in October. So how do I deal with that in terms of like attendance or things like that?
That's something that we'll have to talk about privately once
Okay.
we know what that looks like for you. Yeah, I guess that just depends on the appointments that you have. I'm being pretty chill about attendance because like we're gonna have people who get sick with COVID.
Yeah.
And I don't want to punish anybody for that. That doesn't seem fair. So we'll figure something out. What I mainly want to make sure is that you don't miss any information that you need.
Okay.
And I will record all the sessions and put them up onto YouTube as unlisted videos. So if there is a question like today, I'll accept some late attendance for things like that for students who had reasons to not be here.
Okay. Which can I just email you then the dates and things like that?
Mm-hmm.
Okay. Okay. Perfect. Thank you.
Mm-hmm. Okay. If you're still here and you don't have questions, class is over, but I know I'm waiting on a private meeting. Okay. Now you're good. Let me stop the recording.